Hey calculus people, little video here on some notes on end behavior of a graph. So we've been doing all sorts of stuff about where maxes and mins and increasing, decreasing, x-intercepts, y-intercepts. The one thing we haven't really talked about is what happens way, way out to the right on your graph and way, way out to your left on the graph. So that's called end behavior. Right? Because it's what your graph does at the end. And if you look at this, basically we want to know the limit of our equation as x goes to infinity, and the limit of our equation as x goes to negative infinity. So that's far right, far left. That'll help us graph the picture. All right, so the first thing we can do is kind of just intuition or brute force, and that is if you want to know what happens to this as you get closer and closer to infinity, you can just type it in your calculator with a huge number in there and see what happens, see what it gets closer to. So let's try that real quick. The first one I did was I typed in just 100, which isn't even that close to infinity, right? So we plug that in. Let's turn that into a decimal. Where's that button on here? To math, decimal. Okay, so that's 4.001. We can take that up even another notch and maybe plug like 1,000 in on top and bottom and kind of see what number this squeezes in on. Okay, so I did the exact same equation, but I put 10,000 in top and bottom for x. And look at how close we're getting to the number 4. But what if it was a negative 10,000? So we'll go insert a negative sign. I want to know what happens to it as it goes way to the left also. Oh, geez. Yikes. There we go. So way out to the right, it looks like it's approaching a y value of 4. Way out to the left, it's also approaching a value of 4. So that's the brute force way. I don't want to really use that way, but it's always something you can do. But what's kind of cool is, as x gets really, really huge, this means very little. Because think about it, like if this was worth 4 million, was 4 million plus 5 really going to make much of a difference? No. Same with the minus 2. So these numbers at the back end up being meaningless, and you can treat this problem like, even though this feels like cheating, you can treat it like it was just this equation, because as x gets really, really huge or really, really small, it does behave like this equation. That's not to say you're normally allowed to do that. It's just when it approaches infinity or negative infinity. So don't get carried away with this. And if I reduce that fraction, top and bottom cancel, and you get 4. You do have to be kind of careful with this before you go and put a 4 on both of these. Double check in your brain, like before you canceled out. If I put a big negative number in there, the top would turn positive, right? If I put a big negative in there, the bottom would turn positive. And a positive over a positive is still a positive 4. There are occasions where you'll have the digit right, and one of these will be positive 4, and the other one would be negative 4. Not in this case, but you should always double check your sign if you do this method that kind of feels like cheating. There's a more specific way to do this, but this is the method that most people use to find end behavior. So what does that tell me? That tells me if I were to graph this thing way, way out, I'm not saying what it does in the middle, because it'll do all sorts of weird stuff. But as you go to your graph way, way out to the right, it's going to approach this y equals 4 height. And as you go way, way to the left, it's going to approach this y equals 4 height. It's a little different than a vertical asymptote. This is called a horizontal asymptote. However, what's weird about these is your graph can cross them, and it probably will. Like this graph is going to have maxes and mins and inflection points and stuff, but as you get way out to the right, you know that it's going to like get closer and closer to that. As it gets way to the left, it's going to get closer and closer. Now, I don't know if it's coming from above or from below. We do have a way to figure that out, but not for now. Right now, we're just worried about finding that number that your graph approaches way out to the sides. So we'll do a couple more examples till you get comfortable with this. And before we do a couple more examples, I want you to write down these properties of infinite limits. There's 3 of them. The first 2 are really common sense, and that is the limit as x approaches infinity of f of x plus g of x is the same as if you did the limit of one plus the limit of the other. You're allowed to split up addition if you want. You're allowed to split up multiplication if you want into separate limits. The important one, the most important one, is this guy, because this is going to lead into some of our other tricks later on. As long as r is a positive rational number, then if you ever have c, that's c for constant, over x to the r, I call these bottom-heavy graphs, because there's x's in the bottom. The limit equals 0, and that may seem crazy at first because you're like, you're putting an infinity in there. But imagine if I had 4 divided by 100, right? Pretty small number. Okay, 4 divided by 1,000 or 10,000. That's pretty tiny because that's 0.0004. And then 4 divided by, you can see where this is going. You know, big number, 0.000008 or 4. So basically, the bigger the number on the bottom, the closer to 0 it gets. Well, guess what? If you go to infinity in the bottom, you essentially have created 0. Dividing by infinity makes your limit go to 0. So we're going to use that idea later on. So write those down real quick. All right, so let's try a couple more of these out. Here's one, and it doesn't matter if you ask positive or negative infinity. You've got to check at the end what your sign is anyway. So if I looked at this one, I mean, the official way would be to divide every term by x, and you'll see what happens. But the common sense way says, as x gets to be a number close to negative infinity, so a huge negative number, this minus 4 ends up not meaning much. This plus 6 ends up not meaning much, and you're left with something that's 5x over 3x, which simplifies because x cancels, and it approaches 5/3. Which means as my graph gets way out to the right and way out to the left, they're going to approach this horizontal line 5/3. I don't know if it's from above or below. Before I circle that as my answer, I always want to check the sign. If this is a negative in the original problem, the top would be a huge negative number, the bottom would be a huge negative number, and a negative over negative makes a positive. So I'm cool with keeping that positive. We'll do a problem later where you got to change that at the end. Okay, so this is basically the 3 different options we have. We have one of these graphs that I would call as top heavy, one is bottom heavy, and one is even strength. The ones we just did a couple examples of are ones I would call even strength. Because if you look at the powers, this is the biggest power on the top, and this is the biggest power on the bottom, and they're even. Now it may seem crazy if you put an infinity here and cube it, an infinity here, and a 4, and here you have an infinity cubed, and a minus 7, you would think this would go off to infinity because you have an infinity and an infinity, but what's crazy is how much more of a difference the cubed makes. Even if you did like 10,000 cubed, 10,000, actually let's do 1,000 cubed. You know what 1,000 cubed is? That. Okay, it's 1 trillion. So you can imagine the difference between what 1,000 is and a trillion before you even start multiplying. So this is why we actually get to ignore all these other numbers, even if there's an x involved. You basically get to ignore them. And if they're even strength, you're going to see, every time an even strength one, these whole things go out because x to the third disappears and you approach kind of a normal number. Now before I circled, I should check my number. I have a huge positive on top. I have a huge positive on bottom. That leaves me with a positive answer. Okay, so now we get to one where I would call this one a bottom heavy. Okay, And a bottom-heavy graph, you can tell it's bottom-heavy because it has x a third on bottom and only x squared on top. So we can still do the thing where we ignore the rest of these, even an x squared, which seems crazy, but I promise you, 1,000 squared versus 1,000 cubed is a huge difference. And you can imagine as I get to be like 1,000,000 squared versus 1,000,000 cubed, it's going to make an even bigger difference. I don't even know what number that was. So you can see that's like 1,000,000 times bigger than that one. So anyway, so it just behaves like this. So if I were to reduce this down, 4x squared over 3x to the third, and I canceled off x squared from the top and 2 of those from the bottom, I'm left with this. And this should seem familiar because if there are still x's in the bottom and I put a huge negative in there, it's like that rule from before. If you ever have x's in the bottom and a constant on top, then your answer goes to 0 because it's like I'm taking 4 divided by negative 3 billion, right? That goes to 0 every time. Every bottom heavy graph will result in 0 as your answer. Now technically I would know the bottom would even be a negative number. So you know how I said sometimes you can tell if it approaches from above or below? This one would approach 0 from below. So as I go way left, it approaches 0 from below. All right, and then our last one here is a top-heavy graph. Okay, and top-heavy because it has x to the cube on top and x squared on bottom, so we still get to ignore these because we're going to infinity. And if I were to reduce this, I would be left with 4x over 3. Now, if you plugged in an infinity, you got 4 times infinity divided by 3. Do you think dividing by 3 makes much of a difference to infinity? It does not. And the answer goes to infinity. Double check your sign. On top, I'd have a huge positive. On the bottom, I'd have a huge positive. So the end answer is positive infinity. Sometimes you get a negative in there and it throws things off. All right. So, by the way, every time you have a top-heavy graph, it will either end in infinity or a negative infinity. Every time you have a bottom-heavy graph, it will always end in 0. And every time you have an even strength graph, it'll end in a number. Could be positive, could be negative, you gotta check. Okay, so one last example. Okay, so here's our last one. I want to find the end behavior, so whenever you see that, you can automatically write these two and limit as it goes to positive infinity and negative infinity. So we're going to do the same thing on this one, but this one's tricky. I knew I had to show you one that was tricky. So first of all, you are allowed to ignore this and ignore this, and you're left with 2x over radical x squared, which at first the radical was a problem, but can you take the square root of a variable squared? Sure. This behaves like 2x over x, which reduces to be 2. But be careful, if you just wrote a 2 in both these, you'd get it wrong. Well, you get one of them wrong. Because, think about it, this is where you got to double check at the end. If I put a huge positive number in the original problem, 2 times a huge positive number leaves you with a positive. Here I take a huge positive number, I square it, which makes it even more huge and positive, and then I square root it, which still results in a positive. So this answer is actually correct. But down here you would get it wrong because if I put a huge negative in here and multiply by 2, get rid of those. If I put a huge negative in here and multiply by 2, it is a even twice as big huge negative. If I put a huge negative in here and square it, now it becomes positive. And then when I square root it, it kind of takes it back down to size. So I have a negative over a positive. And if you have a fraction with a negative over a positive, you're left with a negative answer. Just to show you, I graphed this equation in my calculator, and you can see as you go way, way, way to the right, look what y value it seems to approach, 2. And as I go way, 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 way left, look what y value it approaches, negative 2. You could graph every one of your answers and double check that it looks like you think it is. You should. Check the ones with 0, with infinity, with negative infinity, and see if you're getting good with the signs. All right, I'll talk to you later, people. Adios.